streaming.
Okay, guys, welcome to science. Just gonna wait another minute here. I guess not quite 10:30, and then we'll get started on this. Okay, so today, you guys, we're gonna cover. If you look up the top here, it's speed, velocity, and acceleration. And if we were doing this in class, I would have broken you guys into groups. And one group would have basically done what speed is, one group would have done velocity, and one group would have done acceleration. That's how this basically is broken up. So what I'll do is we'll do speed together, then I'll let you do velocity and acceleration on your own. Okay, so it says background for all groups. Groups will present information about relative motion, speed, velocity, and acceleration. So it says take notes, and there's a section here where I'll show you how to take notes. So it says an object is in motion when it's continuously changing its position relative to a reference point observed by a person or detection device. For example, you can see an automobile is moving with respect to the ground. So the distance the object goes in a period of time is its speed. If the speed of the object in a specific direction is called velocity, and the change in time or the change in velocity over a period of time is acceleration. Okay. So basically, think about these questions. Why must motion be with respect to the observer? What's the difference between speed and velocity? And where is acceleration used? So when we're done with this, you'll be able to answer all three of those questions. Okay, so I'm going to go down to motion here. So all motion is relative to the observer to some fixed object. Motion can be described as a measure of the distance an object moves in a certain length of time. So for these are two examples of motion with a bus and a car. For example, when you see a bus drive by, it's moving with respect to you. However, if you are in a car that is moving the same direction, the bus will be moving at different velocity with respect to you. So the car is going one speed and the bus is going another speed. But if you're standing on the sidewalk, it looks like maybe it's going a little bit faster. Because in the car, you're probably moving, whatever, 25, 35 miles an hour when you go by the bus, okay? So if your car is moving in the same direction, same to the bus will appear not to be moving with respect to you because you guys will both be going the exact same speed. So it'll look like the bus is stationary. But if you're on the sidewalk, both the car and the bus look like they'll be moving faster. It says, of course, if you compare the speed with the ground, both of you will be moving at the same velocity. Okay. So this is what I'm talking about. So group A would have done motion. Group B would have done, I think, is velocity the second one. Yep, and then group C would have done acceleration. So, and you can see here, guys, there's notes. So after you read this, you can just kind of jot down some main ideas from this. So like I said, we'll cover motion together, okay? So it says motion. Suppose you saw a person walking to the front of a moving bus. The person will be moving faster than the bus from your viewpoint. However, the person will not notice the speed of the bus while he walks in front. So it's a point of reference. In talking about motion, it's important to indicate your point of reference. In the case of moving automobiles, it's usually assumed the speed is with respect to the ground, but there are situations where the speed or velocity may be with respect to another object or observer. For example, suppose a car was traveling 60 miles an hour and hit another car, but there was hardly a dent. The reason would be the second car was traveling the same direction at 59 miles per hour, so the car was only going 1 mile per hour with respect to the second car when it hit it. Okay, that one's a little bit, that would be maybe if they just bump a little bit, okay? So two cars traveling the same speed. This one says there's a little bit, there's a 1 mile an hour difference, 59. Okay, another example of relative motion is how the sun appears moving across the sky when the earth is actually spinning and cause that apparent motion. Usually we consider motion with respect to the ground of the earth. Within the universe, there is no real fixed point. The basis is Einstein's theory of relativity, that all motion is relative. What do you find as a fixed point? Okay. So for this one, for example, this one's about motion. So the biggest thing is point of reference. So your point of reference is where you're watching. So if you're on the sidewalk watching the car go by, your point of reference is going to be that sidewalk. But when you're in a car, your point of reference is that car. That's why sometimes when you're going, if you're on 490 and there's a car right next to you, you're both going about 60 miles an hour, it really doesn't look like that car is next to you is moving, even though it's going 60 miles an hour, because your point of reference is in the car and you're moving 60 miles an hour too. But if you're on the side of the road, obviously your point of reference is a little bit different, because basically you can see the car moving past you. And basically, if you're going 60 miles an hour, sometimes this happens, and you go, for 1 mile on 490, that car doesn't look like it's moving because you're both traveling the same speed. So that's kind of your point of reference. And keep in mind too, just like if you're in a boat sometimes too, and there's a boat next to you, the same thing, if you guys are both traveling next to each other, obviously it doesn't look the other boat's moving, especially if you're going the same speed. But if you're on the shore, you can definitely tell that boat is moving. Okay, that's the biggest thing about motion. It's just the point of reference. Okay, so after basically, you would just put some notes down here for what you think are important for motion. Okay, then this one is speed and velocity. And when you get done with speed and velocity, you can see there's some notes right here. So I just want you to read speed and velocity and put what you think is important in speed and velocity. And the last one is acceleration. And acceleration starts right here. And then there's going to be some notes right here. And acceleration has some formulas too. So maybe that might be important to put some of the formulas for acceleration. And that brings us down to right here. So if we were in class, the group that did motion would share out what they did for motion. The group for speed and velocity would share out what they put for speed and velocity. And then the group for acceleration would share out what they did in acceleration. That way we could all get notes. We only had to read a third of it. But since we're doing it virtually now, we're doing it from home. I'm just going to have you guys read those on your own, okay? So the summary is motion is a change of position. And it says all motion is relative to some fixed point or object. So that really goes back to the fixed point. And speed is a measurement of that change of position over time. Velocity is a speed in given direction, and acceleration is increase in speed or velocity over time. And deceleration is a decrease of speed or velocity of time. So after you've read all three of those, you will basically be able to understand what all that means. Okay. This next thing here is some problem solving about these three things. So it says solve the following problems. To solve each, write the equation that will be used for work. Work out the problem by replacing the words. Be sure to give the equation with the number of values from the word problem. Finish by solving the answer. Okay, so average speed is total distance over total time. Okay, so a plane travels 1,000 miles. Okay, so that would be the total distance. So it'd be 1,000 over 5. And when you divide 1,000 by 5, you're going to get 200 miles an hour. So that's how fast the plane was going. It was going 200 miles an hour. Okay, this one it's 550 total distance over 4. So you would divide basically 4 into 550, and then you would get 2,200 miles. That's how far it went. Okay, this one, a girl on a bicycle rides down a hill 500 meters in 50 seconds. So the total distance is 500 meters divided by 50. The girl's speed is going to be 10 miles an hour. Okay, This one, 32 miles is a total distance over time in half an hour. So basically, she is going 64 miles an hour because you divide 5 into 32, and that's 64. Okay. And this one's 11 miles over 3, so it's approximately 3.65 miles an hour. So you always put the distance over the time. Okay. And that's how you're going to get out your average speed. It's distance over time. So velocity is velocity equals distance towards time. Okay. So the example here, a plane travels 500 miles east and lands in Arizona, and the plane travels another 500 miles and lands in California. The entire trip was completed in 5 hours. What's average velocity? So it's the 5 plus the 5 equals 1,000 divided by 5. So the answer is 200 miles. This one, you'd have 600 meters plus 100 meters divided by 50. So that would be 700 divided by 50. Okay. So remember, you guys, the biggest thing is just to put the distance. So you have 600 meters and 100 meters over the time, which is, in this case, is 50 seconds. And there's two more that are exactly like that. Well, actually, we're acceleration now. And acceleration is final velocity minus starting velocity over the time it takes to change velocity. Okay. So this one, a runner accelerates from a velocity of 5 miles an hour until reaching a velocity of 10. Okay. So final velocity would be 10. Starting velocity was 5. Okay. So you get 10 minus 5 is going to be 5, and that took 20 seconds. So what you're going to do is you're going to divide 20 into 5, and that gives you 25 miles an hour would be the acceleration. 0.25, excuse me. Okay, so it's final velocity minus starting velocity. So you're always going to get a starting velocity and then a final velocity. And you're going to subtract those and put them over the time. In this case, it was 20 seconds. Okay, this one is 45 is starting, then it goes to 60, and it was in 5 seconds. So you're going to do 60 minus 45 is 15 divided by 5 seconds. So you're going to put 15 over 5, and that's going to give you probably, it took about 30 seconds. Okay, this one, jogging 3 meters a second, 40 seconds later, point B, the jogger's velocity is 1 meter a second. So that's going to be 3 minus 1 is 2, and so it's going to be 2 divided by 40. Okay, and that's going to give you basically 0.8 miles is going to be the velocity there. So if you're confused, you guys, just remember we'll go back up to this one. Okay, so for speed, it's total distance over time. Okay, so the formula is right here. And then for velocity, it's going to be, you're going to add the distance and divide it by the time. So velocity, or excuse me, distance plus distance over time is going to give you your velocity. It's right here. Velocity equals distance divided by time. And the last one, acceleration, is final velocity minus starting velocity over time. So one thing you have to keep in mind, time is always going to be on the bottom. And that's how long it gives you in the equation, okay? So it just asks you to write a speed problem and a distance problem. So, and then you get right here, these are some more ones you can practice. You can have speed equals distance over time, and velocity is distance over time in a specific direction. So that would be either east, west, north, south. Okay, so this is basically, this is 75 miles over 2.5 hours. So you divide 2.5 into 75. This one, an hour to travel 10 kilometers. So these are just basically practice of what we just did. And if you go back up right here on page, I think it's 16, these are all the answers. So this is a plane travels 100 miles in 5 hours. What's a plane's average speed? It's 200 miles an hour. And that goes back up to that first one we did, which was right. Oh, one more up. I'm sorry. Right here. See, 100 miles in 5 hours. It gave you the answer. The first two, they give you the answer. And then down here at the bottom are all the answers. So you can try them on your own, then go ahead and check them right here. And this last one, it says, how do fireworks work? So we'll go ahead and read this. It says the chemical pellets that provide the sparks of light and color in fireworks are called stars. Metallic elements from the stars each emit a specific color of light as they burn due to the difference in their atomic structures. When a metallic element burns, its atoms absorb the thermal energy, which temporarily moves the atom's outer electrons into a higher energy level. The electrons return to their original energy level, releasing a radiant energy and light in the process. The amount of radiant energy emitted, which is unique to each element, determines the color of the light. Light is only visible in forms of radiant energy on the electromagnetic spectrum. The colors of light include red, orange, yellow, green, blue, indigo, and violet. They increase from red to violet on the spectrum. This is what we covered last week. So remember, red is the lowest energy, and violet would be the highest energy. So it says, what metallic energy would you mix to create an orange firework? So orange would probably be, you take the red and the yellow. And purple basically would be kind of the indigo and violet. Okay. This is just basically covering what we talked about the other day about the spectrum. And which element, sodium or copper, releases a higher level energy when it burns. And remember, the more energy, the higher energy is to the right. So sodium is here, copper is here, so it's going to be copper releases more energy. And explain why different metals emit different colors of light, and that's covered right up in here, you guys. So the answer is right in that one right there. And this is just another thing about fireworks, just another, if you can read this and the questions are down at the bottom, and then this is just basically you fill in these vocabulary words into the blanks. And at the bottom here are all the answers for the fireworks question. So once again, if you're having a hard time, you can go back and check the answers at the end. Okay. So I know that's kind of a lot. This was a long lesson, you guys, but this will probably, some of this will probably be covered on the test, especially these formulas, and they'll give you the formula. And this is good because we just covered kind of this in basic math today. It's just kind of basic division problems. And the fireworks thing is just, it's re-going over basically the colors and the energy. Remember, least amount of energy is on the left, higher amount of energy is on the right, and the colors kind of coincide with that. Okay, hope everyone has a wonderful day. I'll be doing social studies here shortly. If you have any questions, just email Casey or myself. Thanks and have a great day. Bye.